Here are Grandpa's hacks to unlimited heat for your home. No electric needed. Oil-based flame heating. Grandpa always said, why depend on grids when liquid fuel can deliver steady warmth on its own? Oil-based flame heating converts stored liquid fuel into controlled, reliable heat without electricity. To use this method, place a safe metal burner or reservoir on a stable surface and fill it with accessible fuels such as vegetable oil, lamp oil, or filtered waste oil. Insert a cotton wick so fuel is drawn upward naturally. Once lit, allow the flame to stabilize before adjusting height. As the oil burns, it releases consistent, radiant heat while consuming fuel slowly. This works because liquid fuels have high energy density and burn evenly over long periods. The result is predictable heat from inexpensive, widely available materials. But producing heat is only the first step. What if that flame could be divided into smaller sources to improve control and efficiency? Distributed wick combustion. A single flame produces heat, but many small flames offer better control. Distributed wick combustion spreads burning across multiple wicks instead of relying on one large flame. To apply this method, install several cotton wicks spaced evenly across a metal burner plate or fuel surface. Each wick draws fuel independently and burns at a lower intensity. As the wicks burn together, total heat output increases while flame stability improves. Smaller flames reduce soot, lower risk, and respond faster to adjustment. This works because multiple low-output flames burn more efficiently than one aggressive flame. Heat becomes smoother, easier to regulate, and more evenly distributed. The system also stays lit longer if one wick fails, but even the best flame needs airflow to function properly. What if air movement could happen automatically without fans or power? Passive updraft airflow. Heat doesn't just warm a space, it moves air naturally. Passive updraft airflow uses the tendency of hot air to rise and cool air to replace it. To use this method, position the flame low within a vertical enclosure or channel that allows air to move upward freely. As air heats, it rises, pulling cooler air in from below and creating continuous circulation. No fans, switches, or electricity are required. Keep exhaust paths open and avoid sharp bends that slow flow. This works because buoyancy-driven movement never stops as long as heat exists. Warm air distributes itself gently through the space while fresh air feeds the flame. The result is quieter, more reliable circulation. But airflow works best when entry points are intentional. What if fresh air were admitted exactly where it's needed most? Dedicated fresh air intake. Every combustion system performs better when it breathes cleanly and consistently. A dedicated fresh air intake supplies oxygen directly to the flame instead of pulling air randomly from the room. To use this method, install a small ductor pipe that brings outside air directly to the burner area. Position the intake low near the base of the flame so cool air feeds combustion efficiently. Keep the pathway straight and unobstructed to reduce resistance. As fresh air enters, indoor air remains warmer and less drafty. Grandpa said that this works because combustion no longer competes with living space air for oxygen. The flame burns cleaner, steadier, and with less soot buildup. The result is improved efficiency and safer operation. But once air is used for combustion, it must leave the system properly. Managing exhaust becomes just as important as supplying intake air. Dedicated exhaust outlet. Burning fuel produces heat, but it also creates exhaust gases that must be removed. A dedicated exhaust outlet provides a controlled path for hot gases to exit safely. To apply this method, install a vertical flue or exhaust channel above the flame that guides combustion byproducts upward and out. Keep the outlet smooth and straight to maintain strong draft. Position it higher than the intake to support natural airflow. As hot gases rise, they pull fresh air through the system, sustaining combustion. This works because separating exhaust from living air prevents backdrafts and smoke leakage. Heat remains where it's useful while waste gases leave efficiently. The result is a cleaner, safer heating setup. But exhausting air safely isn't enough if outside air can leak back in. What if the entire system could be sealed from the room? Sealed exterior venting. Sealed exterior venting isolates combustion completely from indoor air. To use this method, enclose the burner and connect both intake and exhaust directly to the outside through sealed ducts. All combustion air enters from outdoors, and all exhaust leaves the same way. Gaskets or high-temperature sealant prevent leaks at joints. This setup keeps indoor oxygen levels stable and eliminates drafts caused by pressure changes. It works because the heating system becomes independent of the living space air. Indoor warmth stays inside, while combustion happens in a controlled loop. The result is higher efficiency, improved safety, and consistent performance. With air handled cleanly, heat can now be shaped and guided. What if solid materials could channel that heat exactly where you want it? Fuel type flexibility. A reliable heating system must work with whatever fuel you can find. Fuel type flexibility allows a burner to operate using multiple liquid oils instead of relying on one specific source. To apply this method, design the fuel reservoir and wick system to tolerate different viscosities, such as vegetable oil, lamp oil, kerosene, or filtered used cooking oil. Grandpa advised to use wider wick channels and adjustable flame height to compensate for thicker fuels. Pre-warming heavier oils can improve flow. This works because oil combustion depends more on vaporization than chemical precision. Flexibility ensures heat continues even when supplies change. The result is resilience in emergencies and lower operating costs. But fuel flexibility also depends on how consumable parts are handled. What if wicks could be replaced easily and cheaply? Disposable wick media. The wick is the heart of an oil burner, and treating it as disposable improves safety and reliability. Disposable wick media allows quick replacement without maintenance or cleaning. To use this method, choose low-cost materials like cotton rope, rolled cloth, or untreated cotton pads. Cut them to length and insert them into the wick holder as needed. When carbon buildup occurs, simply replace the wick instead of trying to clean it. This works because fresh wick fibers draw fuel more evenly and burn cleaner. Disposable media reduces downtime and prevents poor combustion. The result is consistent flame quality with minimal effort. But steady burning also depends on how fuel is stored and delivered. What if gravity alone could manage fuel flow? Internal fuel reservoir. A heating system works best when fuel is protected, stable, and close to the flame. An internal fuel reservoir stores liquid fuel inside the heater body, keeping it warm and shielded from temperature swings. To use this method, integrate a sealed metal container directly beneath or beside the burner assembly. The reservoir should be made from heat-tolerant steel and positioned so rising warmth gently heats the fuel without overheating it. As the fuel stays warm, viscosity drops and flow becomes more consistent. This works because warm oil feeds more predictably and reduces flame fluctuation. Internal placement also prevents spills, evaporation, and contamination. Refilling can be done safely through a capped port while the system is off. The result is longer run times, steadier output, and fewer interruptions. But storing fuel is only part of the equation. What if fuel could move to the flame automatically without pumps, valves, or electricity at all? Gravity-driven fuel feed. Fuel delivery doesn't need pressure or power when gravity does the work. A gravity-driven fuel feed allows oil to flow naturally from the reservoir to the wick using height alone. To apply this method, position the internal fuel reservoir slightly above the burner or wick holder. Use a short metal tube or channel to guide fuel downward at a controlled rate. As fuel is consumed at the flame, more flows in automatically to replace it. This works because gravity provides constant, predictable movement without mechanical failure points. Flow can be fine-tuned by adjusting wick thickness or feed height rather than using valves. The result is silent, reliable fuel delivery that never depends on electricity. With fuel feeding itself steadily, attention can shift to safety and control. But how do you monitor a flame you can't clearly see? Flame viewing port. Seeing the flame is essential for safe, controlled heating. A flame viewing port allows visual inspection without exposing the burner to open air. To use this method, install a small window made from heat-resistant glass or mica into the burner enclosure. Position it at eye level where the flame is clearly visible during operation. The sealed window lets you monitor flame size, color, and stability in real time. This works because visual feedback allows immediate adjustment before problems develop. Yellow smoke, flicker, or uneven burning can be corrected early. A viewing port also adds confidence and control, especially during long burns. The result is safer operation and better tuning. But the flame does more than create heat. What if light itself could become a useful byproduct of the system? Integrated light output. A flame naturally produces light, and using it intentionally adds value without extra fuel. Integrated light output captures illumination from the burner and directs it into the living space. To apply this method, position reflective metal surfaces or a heat-resistant glass chamber around the flame so light is projected outward safely. The enclosure should allow brightness to escape while keeping the flame sealed. This works because combustion already generates visible light, which is normally wasted. By shaping and directing it, the system provides both heat and illumination at the same time. Light levels can indicate flame health with steady brightness, signaling proper combustion. The result is reduced dependence on separate lighting sources and improved efficiency. Heat and light working together create both warmth and comfort. But sometimes air movement needs a little assistance. What if minimal power could enhance circulation without breaking off grid independence? Low wattage air mover. Natural airflow is powerful, but small assistance can improve distribution, said Grandpa. A low wattage air mover gently boosts circulation without significant energy use. To use this method, install a small DC fan near the upper heat zone where warm air collects. The fan should run at very low speed, just enough to nudge heat outward. This works because moving warm air slightly prevents heat pooling near the ceiling. Power requirements stay minimal, often under a few watts. The system remains mostly passive while gaining better room coverage. The result is more even temperatures with almost no energy cost. But running even small electronics requires thoughtful power choices. What if the entire system ran on simple, safe electrical standards? DC-only electrical system. Keeping power simple improves reliability off-grid. A DC-only electrical system avoids inverters and complex electronics. To apply this method, power fans, sensors, or lights using 12-volt DC from batteries or solar sources. Use short wire runs and simple switches to reduce loss. DC systems are safer, easier to repair, and more efficient at low power levels. This works because many small devices are designed to operate directly on DC. Eliminating AC conversion reduces failure points. The result is dependable operation even during outages. With electrical needs simplified, attention can shift back to managing heat safely, but components near flames still face high temperatures. How can they be protected long-term? Air-cooled structural parts. Heat creates warmth, but it also stresses the structure that holds it. Air-cooled structural parts use moving air to protect critical components from overheating. To apply this method, design gaps, channels, or vents around metal supports, housings, and mounts so air can flow freely across their surfaces. Position intake openings low and exhaust openings high to encourage natural airflow. As cooler air passes over hot parts, it absorbs excess heat and carries it away. This works because air movement limits temperature buildup and prevents metal fatigue over time. Even passive airflow can significantly extend component life. The result is a system that runs cooler, safer, and longer without added complexity. But heat doesn't only threaten the heater itself. Nearby walls and surfaces also need protection. What if heat could be safely blocked before it ever reaches them? Fireproof wall shielding. Any heat source near a wall needs a barrier that can take the heat without failing. A fireproof wall shielding protects surrounding structures while reflecting warmth back into the room. To use this method, install fire-resistant boards, such as cement board, metal sheet, or ceramic paneling between the heater and the wall. Leave a small air gap behind the shield so heat can dissipate upward instead of transferring directly. This works because fireproof materials resist ignition, while the air gap reduces heat conduction. The shield stays cool enough to protect framing while still allowing radiant heat to spread forward. The result is safer placement options and improved heat efficiency. But shielding alone isn't enough if spacing is inconsistent. What if distance itself became a fixed safety feature? Fixed clearance mounting. Safety improves when spacing never changes. Fixed clearance mounting locks the heater at a known, safe distance from walls and floors. To apply this method, use rigid brackets, spacers, or frames that physically hold the system away from nearby surfaces. These mounts should be made from metal or other heat-tolerant materials and installed permanently. So by fixing clearance, accidental movement, or settling can't bring hot parts closer to combustible materials. This works because predictable spacing eliminates guesswork and reduces fire risk. Air can circulate freely, shielding remains effective, and heat behaves as expected. The result is consistent performance and peace of mind. With placement secured, attention can shift to capturing and storing heat itself. Radiant heat storage surface. Heat is most valuable when it lingers instead of disappearing the moment fuel is reduced. A radiant heat storage surface captures excess warmth and releases it slowly, extending comfort without additional fuel. To use this method, place a dense material such as cast iron, thick steel plate, stone, or ceramic directly above or surrounding the flame path. As the burner operates, the surface absorbs heat gradually instead of letting it escape immediately into the air. Once the flame is lowered or extinguished, the stored heat continues radiating outward for an extended period. This works because high-mass materials have the ability to store thermal and energy and release it evenly over time. The result is smoother temperature control, fewer sharp heat spikes, and longer warmth between refueling cycles. A storage surface also shields sensitive components from direct flame exposure, improving durability. With heat now being stored intentionally, the next challenge becomes knowing exactly how hot different parts of the system are at any given moment. Multi-point temperature checks. A heating system performs best when temperatures are understood rather than guessed. Multi-point temperature checks provide insight into how heat moves and where it builds up. To apply this method, place simple thermometers or heat indicators at key locations such as near the flame, along metal heat paths, at the exhaust outlet, and on outer surfaces. During operation, compare readings to identify hot spots, airflow restrictions, or inefficient heat transfer. This works because temperature differences reveal problems before they become dangerous or wasteful. Consistent monitoring helps fine-tune airflow, wick height, and heat storage placement. Over time, patterns emerge that show which configurations produce steady warmth and which cause overheating. The result is improved safety, longer component life, and better efficiency. Knowing temperatures also builds confidence when adjusting the system. But heat control isn't only about temperature, it's also about understanding how fast fuel is being consumed over time. Fuel burn rate logging. Efficient heating depends on knowing how much fuel is used, not just how warm it feels. Fuel burn rate logging tracks consumption to improve consistency and extend run times. To use this method, record the fuel level before lighting the system and note the time it takes to reach a specific reduction point. Repeat this process under similar conditions to build reliable averages. This works because burn rate data reveals how wick height, fuel type, and airflow affect consumption. Over time, adjustments can be made to favor longer, steadier burns instead of fast heat spikes. Logging also helps predict refueling intervals, reducing interruptions and waste. The result is a system that runs longer on less fuel with predictable output. Understanding burn rates turns heating from guesswork into a controlled process, allowing warmth to be managed deliberately rather than reactively. Extended burn bias. Fast, intense flames create quick heat, but they also waste fuel and shorten system life. Extended burn bias focuses on producing steady warmth over long periods instead of chasing rapid temperature spikes. To use this method, lower wick exposure and fine-tune airflow until the flame burns small, stable, and consistent. Avoid pushing the system to maximum output. A calmer flame allows fuel to vaporize evenly and burn completely. This works because slow combustion extracts more usable heat from each unit of fuel while reducing soot, smoke, and component stress. Heat storage surfaces have more time to absorb energy, and airflow stays balanced. Grandpa said that extended burns also reduce the need for frequent refueling and constant adjustments. The result is smoother indoor temperatures, quieter operation, and improved fuel efficiency. Instead of dramatic swings between hot and cold, the system settles into a reliable rhythm that can run for hours. Once burn duration is optimized, The next improvement comes from deciding where that heat should go. What if concentrating warmth in specific areas could make the entire setup feel far more effective? Localized heating focus. Heating an entire room evenly sounds efficient, but it often wastes energy where no one is present. Localized heating focus concentrates warmth exactly where people spend their time. To apply this method, position the heat source near seating, sleeping areas, or workspaces instead of trying to warm the whole room. Use metal reflectors, heat channels, or barriers to direct radiant heat toward the body. Close doors, hang curtains, or block unused areas so warmth stays concentrated. This works because a smaller heated zone reaches comfort faster and retains warmth longer. The body feels warmer even if surrounding air remains cooler. Localized focus pairs naturally with extended burn bias, allowing steady heat to build in one place instead of dispersing thinly. The result is higher comfort with less fuel. By heating people instead of empty space, limited energy produces a noticeably greater effect. Manual flame tuning. Automatic systems react after conditions change, but manual flame tuning keeps control in your hands at all times. Manual flame tuning is the practice of adjusting flame size, shape, and behavior deliberately based on real conditions rather than presets. To use this method, observe the flame regularly through the viewing port and make small adjustments to wick height, fuel exposure, and airflow. According to Grandpa, a taller flame increases heat output, while a shorter flame favors longer burn time and efficiency. Watch flame color closely. A steady, clean flame indicates proper combustion, while flicker, smoke, or excessive yellow signals the need for adjustment. This works because combustion responds immediately to physical changes, allowing fine control without sensors or electronics. Manual tuning also adapts easily to different fuels, room sizes, and weather conditions. The result is a system that stays efficient, safe, and responsive throughout long burns. Instead of letting the system decide for you, manual tuning turns heating into an active skill. When resources are limited, the ability to adjust by sight and feel becomes invaluable. Mastering the flame ensures warmth is delivered intentionally, not accidentally. But even the most well-tuned system matters little if it depends on fragile infrastructure. That leads to the final priority: off-grid operation priority. A heating system only truly works when it functions without external dependency. Off-grid operation priority means designing every part of the system to run independently of utilities, networks, or complex supply chains. To apply this principle, favor gravity, buoyancy, manual controls, and low-voltage components over powered automation. Use fuels that can be stored long-term, sourced locally, or substituted easily. Electrical needs should be minimal and limited to simple DC systems powered by batteries or small solar setups. This works because independence removes single points of failure. When outages occur or fuel access changes, the system continues operating. Maintenance becomes simpler, repairs are possible with basic tools, and operation remains predictable. Off-grid priority also encourages efficiency because wasted energy cannot be easily replaced. The result is resilience. Heat remains available regardless of weather, grid status, or supply disruptions. By placing independence above convenience, the system becomes reliable under pressure. In the end, endless heat is not about complexity. It is about control, adaptability, and freedom from dependence. For more contents like this, click here to subscribe.